Yeah, okay. Anyway, I mean, today I have a lot of slides, but some of them will be just left for offline consultation, because somehow yesterday I was lower than I wanted, and so there is a lot of material, but I'll try to go through that as best as I can. So let me see. Okay, so today we are going to discuss three things: how we go beyond point estimates and systematic uncertainties, and then p-values, significances, and all of that. So so far we've been, when talking about inference, we've been talking about so-called point estimate, which is a technical word to just say that we quote a center value with uncertainties. That's it. I mean, it's nothing exotic. And so, however, in this quoting of point estimate, there are important details that we need to figure out and make sure we understand, because otherwise we could, mislead our peers that look at our result. And those details are, for instance, if the estimator is biased, how should I treat or estimate the biases? We know that the maximum likelihood estimator is actually biased. Typically, those biases are small, but sometimes they're not, especially when the likelihood is not in the asymptotic regime of an infinite number of observations. And the other important thing is whether the procedure that provides our result is able to guarantee the desired coverage. So yesterday we saw that coverage is a very important, probably the most important property of a result in physics. And so it's good to wonder, whether the procedure we are using guarantees coverage. And to give an example of this, a very simple example, you can take the case of estimating an efficiency, right? You want to estimate an efficiency of, let's say, a detector. And so you have a control sample and you serve the number, which we call N of the successes out of an n-tot number of trials, okay? And then you construct an estimator of the efficiency, which is just this this row here, which is the ratio between the successes and the trials. And there is, nothing new here. And then suppose that you execute your experiment, you observe 3 successes on 10 trials. And then the obvious question is, what's your efficiency and what's the uncertainty on that, okay? So you probably know or should know that an estimator of an estimation of an efficiency is basically a binomial estimation, because the efficiency is a binomial quantity whether as you either succeed or not. And so therefore what people usually does is that it replaces the number of successes and the number of trials into this estimator row hat and get, of course, 0.30, okay, 30% efficiency in this very experiment. And when it comes to determine the uncertainty for that, so the standard deviation of this efficiency, typically what you would be led to do is to take the binomial uncertainty on the efficiency. So you have this formula here, and you obtain the interval row 1 to row 2 or the point estimate row hat plus or minus sigma. And what you see here is that it's very easy to get to paradoxical result, because if you're measuring an efficiency that is very close, for instance, to its bounds, so you measure, for instance, you have a number of successes that is a 0, or a number of successes that is actually equal to the number of trials, so you have 10 out of 10, then this flawed estimate of the uncertainty is actually 0. So you would be measuring an efficiency with absolute certainty, with no uncertainty, which is of course not possible. And so this is one of the many examples one can use to show that in order to guarantee coverage and to give results that make sense, one sometimes need a further step in abstraction. And so we are now attacking what are called the confidence intervals, which means giving results of measurements, not in terms of a central value plus or minus an uncertainty, but basically morphing this into an interval that brackets, covers the true value with a certain confidence level. And basically we are trying to answer the question, if I'm given a model, what are the values of the unknown parameter m for which the observed data in my experiment, x0, are among the least extreme possible values of x, okay? And so to specify what extreme is, one needs an ordering. And so once have a ranking of values, which is according to possible criteria, and based on that, one defines a confidence interval. And I will show you in a second how one does that. So in this particular case, this is a toy examples. You see here the distribution of the PDF of some quantity x given a true value. So if you want to set an upper limit on the parameter m here on the top, then extreme values are high values of x, right? High values of data, and therefore you actually start accumulating your values of data from up to lower values until you have basically accumulated a set of extreme values. And the same thing you can do if you want to go to quote a lower limit here on the left, but you do, sorry, on the middle, but you do it starting from the left. If you instead want to quote a central confidence interval, then you start accumulating from both extremes until you have in the center the right amount of probability, which is chosen arbitrarily. It could be 68% if you want a 1 sigma confidence level interval. It can be 95.5 if you want 2 sigma or more. And so this was basically invented by Nyman, and Nyman found a rigorous, mathematically rigorous procedure to construct confidence intervals that have the property of guaranteeing coverage. So they were insensitive to any bias, and they were protected from under coverage, because they were constructed in such a way that the procedure guaranteed that the results cover the true value with the desired confidence level. So how do you do that? Well, there are 2 steps. Before looking at the data, you have to construct what is called a confidence band. And then you observe the data, and from the data and the confidence band you previously constructed, you extract the confidence interval. So let's see this first step of constructing the confidence band. You have here the distribution, the PDFs of the data x for various possible values of the physics parameter m. So you have a distribution from m0, you have a distribution from m1, a distribution for m2, etc., etc. You can generalize that, right? And then take one value, just one value of the physics parameter. Just take the case of m0. You have this distribution, and you decide that you want, in the end, as a result, you want to set up confidence interval at 1 sigma, for instance, confidence level, right? So if you want that your result have 1 sigma coverage, then you choose in this distribution, you choose a 68%, you choose the range of x for which the integral is 68% of the total, okay? And of course, this choice is not unique, it's arbitrary, right? You can take it central, like here, or you can take it from extreme lower values, like here, okay? And And then you have also to decide what's the ordering rule, what's the criterion for which, by which you choose this to accumulate data until you reach the proper integral size. So if you do that in various, for all the possible true values that you want to construct your confidence bell on, you will have a situation like this, right? I mean, this is of course a sketch. You have to imagine that you have this for every possible m value. And therefore, you can somehow define in this space of x and m the region that connects, the green region here that connects all the x ranges corresponding to the desired confidence band. Okay, and you see here in this picture that I try to represent that. Now you have basically constructed your confidence belt, and you can basically look at that in this thing where I got rid of the models. And at this point is where we look at the data. Okay, we actually look at the data, because so far in the construction of the green band I didn't look at the data, but now I looked at them. And looking at the data, what does it mean? It means basically to choose an x value, right? That could be a maximum likelihood estimator in our data, and I call it x0 here. And this defines a vertical red line here that will intercept the confidence band. This intercepts the confidence band, and basically what you get is that the range in the true parameter m corresponding to in the intersection between our data and the confidence band, this range here between m minus and m plus is actually the result of our measurement. So is the confidence interval corresponding to our data x0. Okay? And of course, if I repeat the measurement, I would have another set of data different from x0 in general, and I would have another confidence interval, another set of values m minus and m plus. And again and again and again. But the thing is that this set of possible results, if constructed through this procedure, are actually guaranteed to cover the true value of m with the desired confidence level, which in this case has been chosen to be 68%, but it could have been 9 and 95, etc. So this, I mean, if you, of course, I don't pretend that all of you picked that online. You have to think a bit, you have to stare to this a bit and try to understand. And because there is somehow a shift from parameters, from data to true parameters, when one construct in one dimension and then reads in the other. And this requires a little bit of thinking to convince oneself that, that this works. But it does, because if you see it in this example where I have on the vertical axis the true parameter and the horizontal axis the data. So suppose that someone tells you that the true value of the parameter you're trying to measure is m0, right? So someone have measured already with infinite precision and tells you, then if the true value is m0 and you have constructed your band previously, you can have various possible measurements. No? For each x, you have a confidence interval, which are these vertical segments. No? And you see that these vertical segments are the possible confidence that I could get in a measurement, and they are, you know, red or green. And the red ones are the confidence intervals that do not include the real true value, m0, and the green ones are those that include the real true value, and you see that from the graphics here. So since the probability of observing data yielding a green interval is equal to the confidence level, so it's equal in this case to 68% by construction, and since the green intervals do contain M0, then the logic tells you that any observation yields an interval that includes the true value with probability confidence level. So probability 68% in this case. And this is exactly the mechanism by which this procedure guarantees coverage, because by construction, I have a fraction of my possible result equal to the confidence level I set that contains the true value with that probability. Of course, this looks very confusing, and I have here an example with colored balls, similar, although a little bit more complicated than one we had yesterday. And I suggest that you work this example yourself based on my slides, which should be quite self-consistent and explanatory, and convince yourself that the thing that I'm doing here is exactly the same I did in the explanation so far. So again, here you have, the true fraction of white balls. So you have various bags with different fractions of white balls, class A as 1%, class B 5%, etc. And this, the true fraction of white balls is the unknown parameter M. And then I take one random bag and I pick 5 balls, and I'm trying to infer from the color of these 5 balls which class of bag I did choose. Okay, so the number of white balls observed is my data, is my X, and the class is my M. And since I know a priori what is the fraction of white balls in each bag, I can compute for each possible data the fraction, the probability for observing. So if I take a bag of class A that has 1% white balls, I know that. Therefore, if I pick 5 balls, the probability of observing 0 white balls is at around 95%. And then the probability of observing 1 is about 5%, etc., etc., etc. So I have this is my model, I know that. And then I start constructing my confidence belt. And I do it just as I said before, and I invite you to look at that offline and convince yourself that you understand it. So I construct my confidence band. Here I have my confidence band complete. And so far I haven't yet observed the data, but then I go and actually look at the data. So I take one random bag and I pick my 5 balls and I observe, say, 1 white ball out of 5. So this is my observation. This is the red X0 that I had in my previous diagram. And you see immediately that with this observation, I have class A, B, and C that belong to my confidence belt, and class D and class E that do not. Therefore, it means that class D and class E are excluded at 95% confidence level. So I can say at 95% confidence that the bag that I picked was not of the type D or the type E. Of course, these examples are simplified, and you have to think this in a more general way. So X and M, they do not need to have the same unit, they do not need to have the same range, they do not need to have the same dimensionality, and they do not need to be one proportional to the other, okay? But to explain at least the idea, it helps reducing the problem to its essence, basically. So again here, if you now map back this procedure to your efficiency determination, you will have a proper result, a result where the efficiency has an uncertainty, a proper uncertainty, even if the estimation of the efficiency is close to its boundaries. And again, I leave you here to work out the mathematics. It's pretty simple, it's pretty self-explanatory, and feel free to send me email if nothing if something is not clear. Unfortunately, today I have to be a little bit faster, my last lecture, so I don't have the time to walk you through this, but I would be happy to do it offline if that helps you. So you probably notice, even if the procedure is a little bit complicated, you probably notice that there are some arbitrariness. There is some arbitrariness involved here. One obvious arbitrariness is that there are, many choices to choose a range of data X that yields an integral equal to the desired level of confidence. I mean, I can take a central region, I can take an extreme left or right region, I can take some bands, I mean, I can do whatever, but in order to achieve the most precise and informative measurement possible, I better consider the extreme criteria that I mentioned before, and also avoid to have disconnected region, like in this case here. From the mathematical point of view, the only requirement is that the region of the true parameter outside of, the region of the data outside of the band should be, should sum up to 1 minus the chosen confidence region. So if I'm doing a 2 sigma region here, I want that the region outside of the band is equal or smaller than 5%, for instance. And then it's obvious to ask yourself, well, but what is, if it's arbitrary, is there any particularly useful criterion I can use? Well, in the past, for various years, people have used the probability, so-called probability ordering. So they tried to start accumulating probability from the peak of this distribution and going, close to the peak, to the right and to the left for central region, because if you start from the peak, chances are that your X, your data range that you obtain will be the shortest one. And therefore you can imagine that your inference in the end will be the most precise. However, I hope you remember in our first lecture that I told you that the probability actually depends on the metric of the observable X. So if I'm using a different metric, the peak will be in a different position. So there is really nothing, physically, special in using a probability order. It's just a choice that depends on the metric. Therefore, it doesn't have any special properties from the statistical point of view. And there is, another issue which is more serious here, which is the fact that depending on the observation one has, one could have an empty confidence interval. So one could measure basically nothing. And this, of course, is not very comfortable. How does it happen? Well, suppose that you are measuring, you have something that is distributed as a Gaussian, okay, centered at 0, so close to some physical boundaries, and this Gaussian has a finite measurement resolution, okay? So if you have a Gaussian centered at 0, and this Gaussian has some width, it may happen that sometimes you sample values from these Gaussians that are negative, of course, because the width fluctuates to negative values, and therefore you might pick negative values. And that's nothing wrong with that. That could be, even if the quantity you're measuring is defined as non-negative, like a neutrino mass square, if the apparatus you use as a finite experimental resolution, you could have central values that are negative, although they should still be compatible with 0 within the uncertainties, but the central value can be negative. And so if you apply your Neyman construction to this example here, you have this green band that you have constructed, and then you observe the data. And suppose that you observe the data at around -2. So you see this red arrow here on the left. In this kind of observation, you see that the observation has no intersection with the confidence band. So having no intersection, you cannot project into the vertical axis anything, and therefore your measurement has no results. The final confidence interval is empty, and this is clearly not, this is clearly a problem, of course, right? So that's why these two people have have invented a method that in fact was already known but not very popular, of circumventing this. And in this method, they prescribe a specific ordering, so a specific way of choosing your data X to accumulate the probability, to accumulate the integral of P of X given M until finding the right confidence level. So this is when you construct a band, when you have to construct this green thing that I just showed you, you have guidance from this, from these people, and they say that the best way to construct that is to use a ratio. And this is a likelihood ratio between the value of at each, so when you construct your band, you construct it for each true value of the physics parameter. So for each true value of the physics parameter, in this case M0, for instance, you accumulate data to construct your green band in decreasing order of the 8 of your likelihood at M0 divided by the 8 of your likelihood at its maximum. Okay, so this is, I'm trying to express this in this picture here. Again, this is not very easy to pick up online, but you can have a look and try to understand that. So the accumulation score of each element in X, of each element in the data space, no longer depends only on the model for that piece of data at that value M0 of the true parameter, but also at other values of the true parameters, because I'm making a ratio. And if you do that, for instance, in the anyone has a question?
In the previous slide, can you please explain again what is MCAP?
Yes, MCAP is the value of the physics parameter M that maximizes the likelihood for that piece of data. So you have a piece of data here. This is the value of the likelihood at M0. This is the maximum likelihood, the value of the likelihood at M hat. And you take this 8 divided by this 8 as your, ordering parameter. Does that answer your question?
And so this is helping in arriving at optimal value of the green band.
Exactly.
I'm not able to correlate how it is helping.
Yeah, the reason is beyond the scope of this discussion. The reason is that the likelihood ratio itself, and you will see, it's a quantity that have very important and deep statistical properties, and therefore it's for instance, is the best quantity you would use if you are cutting, if you have to apply a cut to separate two classes of events, and this somehow reflects also in this construction. And the reasons for that are, are not difficult, but they're kind of hard to be explained in this lecture. So maybe if you're curious, we can interact offline, and I can point you to the literature. But
okay, thank you. And another thing, I mean, I have seen a lot of measurements, and most of them in physics, they have for some reason at 95% confidence level, at 95% confidence level. Is it just, is there a bias in me looking at it that I had only looked at the 95% confidence, or is there some meaning to that particular level? I mean,
no. The choice of the confidence level, which has to be made before looking at the data, is completely arbitrary, and it's usually made based on what kind of scientific message you are expecting to give, right? I mean, if you're excluding an exotic signal, you might think that giving a tighter exclusion, a more stringent exclusion, so 95 rather than 90, it's more informative for the phenomenologist or your colleagues, etc. And if you're quoting a central value, usually you do it. Sorry, if you're quoting a central interval, you choose it to be at 1 sigma, because that's the conventional standard. I mean, there is no point in giving a result that is valid at 37% confidence level. You just choose 68 because everybody expects 68, but that's arbitrary.
Okay, thanks.
Okay, so the result of this in the toy example I've just shown is that, as you see now, the band constructed according to the likelihood ratio, or the Feldman-Cousins, it's the same thing, will no longer sharply die before -2, but it will, regularly deflect, and this will take into account also observations that are, negative, and will give actually a confidence interval that is not empty for any observation one will do. So this is actually what we wanted to fix, and it does fix it. Of course, there are, it's not absolutely rigorous. There are some paradoxical cases where you still get empty intervals, but in most practical problems, Feldman-Cousins is actually the way to go here. And also, please remember, I'm using this plot to remember you that sometimes you might be puzzled when you measure something that is defined to be non-negative, like the square of a mass or something, you might think that you cannot get a negative central value. But in fact, if the resolution of your experiment allows for that, negative values are completely allowed. And if you do not allow them, if you somehow clip your likelihood to avoid them, you're actually biasing your measurement. So it's perfectly logic to have a negative value for something that's defined positive, a negative central value, provided that the uncertainties are compatible then with 0. So this is a slide that tries to give an operational algorithm on how to construct a confidence level results using the Feldman-Cousins. I'm not going to go through that. I really suggest you to look at the original paper by Feldman and Cousins. It's not very difficult, and especially in table 1, they actually work on, I'm not sure whether it's the original paper or this other talk, but still, they actually work step by step the construction using a Poisson example. And this table here is meant to guide you. And if you devote an afternoon to work out this, you will further fix in your mind. Oh, sorry, full screen. You're right. You will further fix in your mind the actual procedure. Also, I want to give to you, especially to the experimentalist among you, some kind of a tip. Feldman-Cousins, if you have to construct it by yourself from scratch, it involves quite a lot of work, because you have to produce many toy simulation to build those curves from which you start accumulating, etc., etc. But in the very paper of Feldman and Cousins, there are actually very useful tables that you can use in your measurement to have at least a feeling of what would be the results, the sensitivity of your measurement. And those tables are bought for, counting experiments in which, the intervals are based on a Poisson case, but also they are for the Gaussian, the Gaussian cases. So if you're doing a fit of a signal and you see basically a yield that is compatible with 0, you want to set a limit, and you can use those tables here to guess what your limit would be. Especially, of course, you have to check that your estimator is distributed in a Gaussian way, but that can be done with a simple toy, and then you can use this table here. So I said another shortcut, in addition to those tables, is to use an important property of the likelihood ratio. Remember, the likelihood ratio is the quantity that is used as ordering principle in Feldman-Cousins approach, and this quantity has the important property that its sampling distribution is known. So we know that the likelihood ratio, is distributed as a chi-square, and we know that this happens independently of the shape of the P here, independently whether P, is Gaussian or something else. The likelihood ratio is actually a very good approximation for many problems distributed as a chi-square. So this means that you do not need simulation to construct the distributions where you then select your bands to construct your confidence band. You can actually assume, in many cases, or at least verify, but then assume that the likelihood ratio is a chi-square distribution, and this saves you a lot of work because you can use the tabulated curves of the chi-square and then use, see where the likelihood ratio that you observe in your data falls along, the appropriate of these curves. And once you see that, you immediately have, a measure of you immediately have actually a Feldman-Cousins band for that particular value. And this is basically the thing that also the MINOS algorithm in the min-width minimizer that people doing fitting uses to calculate the uncertainties. So what MINOS does is to move away from the maximum of the likelihood here in the plot, and to move away until the ratio between the maximum and the value probed is corresponding to a particular confidence level according to the chi-square curve. And once you do it, you have your uncertainty set, and those uncertainties have proper coverage because they are extracted according to the likelihood ratio principle. I don't know if Jim yesterday discussed that in the tutorial. I hope yes, because I'm sure that this explanation now is a little bit too obscure for you.
I used it and mentioned that this would come today.
Okay. Yeah.
And so hopefully it is a little clearer now. I think it did cause a bit of confusion yesterday moving to this.
Yeah, it is, but probably I'm not sure how my explanation will clear the confusion. But the idea is that the idea is the following. The concept is simple. Using the likelihood ratio is a good ordering principle to build your confidence interval, and therefore to quote your uncertainties. And you can do that, by first principle. You can construct your sampling distribution of your estimator and then accumulate data until, reaching probability, as I showed you with my sketches before. Or, there are some shortcuts in some special cases where statistics, where you have enough observation, you exploit the fact that the likelihood ratio, the Feldman Gaussian quantity, is actually distributed as a chi-square curve. So since we know the chi-square curves, we can construct our bands without generating much simulation, just using the tabulated values. I see that there are 3 questions in the chat. Can we use some other method except chi-square for likelihood fit? Yes, absolutely. You can. I mean, is this question related to the confidence band construction? For the confidence band construction, you need the likelihood, basically. You need the likelihood. This is based on the likelihood. But if you're estimating a parameter, you can use whatever method you want, provided that it has convincing properties that will show your colleagues that what you did is good. Does it convince you?
Okay, so then for confidence, if we find the result with error, then we should use the chi-square fit.
No, sorry, I'm not sure I got it. You can use a chi-square fit. You can use a chi-square fit, a least square fit, and you will have, you will have the properties that we discussed yesterday briefly. So you will probably have a little less precision than a likelihood fit, but you will gain the fact that you know the goodness of your fit to the data. Does this resonate?
Okay.
All right. Thank you. So let me go quickly. Oh, I have this thing. Let me go quickly to another important concept, which is the one that so far we have been talking about, statistical uncertainties. So the uncertainties that are associated with the fact that I only observe a subset of the parent, of the data from the parent distribution. What are the systematic uncertainty that you probably have heard about? So the systematic uncertainty are those that account for the differences between the model we assume and reality, okay? In any problem, we are assuming a model using the best of our knowledge and the best of our intuition, but of course, this model is a simplified model that will actually, approximate some of the effect at play. So if our assumed model is this thick, curve here, we can very well, imagine that the real unknown theory is something close to that, but not exactly identical, okay? And so one can parameterize that by imagining that even if I assume my model to be P of X given M, the real model will be something that depends also on an additional set of parameters, nu. So the real unknown theory will be P of X given M, comma, nu. And this basically means that not only I don't know which data X I will be observing for a given true value, but I don't even know exactly with which probability the various possible X values are observed. So there is an uncertainty on the probability, on the shape of the model, okay? So how systematic uncertainty is interpreted? Well, usually you see point estimate of the form, our result is 10 plus or minus 4 statistics plus or minus 3 systematics, okay? And what people does is to sum in quadrature statistics and systematics because, they assume them to be independent and give us a result with a total error. And your colleagues will interpret this total error in a statistical way, even if it's not justified. And they will imagine that your interval, in this case, you know, m between 5 and 15, will contain the true value of m with 1 sigma probability, with 68.3% probability, okay? And if you want that their interpretation to be correct, if you want that the communication is consistent between you who produce the results and those who read it, you have to make sure that, therefore, that your result covers the true value independently of the uncertainties in your model. So independently on the real value of those new parameters that are present in your model and that, you know, make it deviate from your assumption. So that's why it's important to report detail on how systematic uncertainties are assessed, and also to make sure, as you know, as much as possible, that your measurement, including systematic uncertainties, still has coverage, because this is most probably how people will interpret it. And if it doesn't coverage, then it's prudent to actually write it clearly in the documentation. So there are, you know, we have introduced these additional abstract parameters new to parameterize the difference between the assumed model and the ideal, the real model, right? And there are two cases. One case where I don't know the value of nu, but I know how nu is distributed. So I know the probability of x given nu. And there are cases where I do not know how nu is distributed. So I do not have any idea of the distribution of nu. I don't even know if it has a distribution, because if it's a theory parameter, in a frequentist approach, it doesn't have a distribution, it just have an unknown value. So in the first case, where the distribution exists and it's known, for instance, because nu is the result of an auxiliary measurement, and therefore one can assume it to be approximately Gaussian, in those cases, this nu is not properly a systematic uncertainty. It's actually an opportunity to refine my model, because I could put in my likelihood the known distribution of P of X given nu and have a better, you know, a better inference, a better estimate. So these cases are, I would like to classify them rather, you know, more like model refinements than systematic uncertainties. And then there are cases where actually the probability is unknown. You do not know how your data depend on nu. You do not know P of X given nu, okay? And this can be many cases. They can be shape parameters of your model, can be theoretical parameters that do not have a distribution, etc. And the treatment of this case is not straightforward. So Bayesian approach, you know, guess what, is very, you know, it's very consistent here. And they treat those new parameters just as they treat the physics parameters. So they assume a prior, P of nu here in my second paragraph, and then integrate the full model P of X given mu comma nu multiplied by this prior in the space of the new parameter, in the space of the systematic. So this is called marginalization. And as you see, the result you get is a model P of X given M that no longer depends on the unknown parameter. And I guess now you should be already familiar with the fact that this thing is very consistent. This thing is probably, you know, convenient, but of course it has two possible drawbacks. The first one is that you're introducing subjective input because you're assuming a distribution for nu that you didn't know. And the second is that there is no guarantee that the final result contains the true value with the desired probability content. So this might be a problem in interpretation of your results by other people than you. The frequentists do a different thing. They try to find plausible extremes for the model. And I've shown in this picture what a plausible and implausible means. So you have an idea, of course, that's also subjective, but you have an idea that your unknown parameter can be somewhat bracketed within a certain range, for instance. And then what you do is that you make sure that your inference give coverage for any value of your nuisance parameter within that range. Okay, so you repeat, you do your inference, you do your measurement, assuming that your nuisance parameter has the worst possible value for your inference, and make sure that your procedure has coverage there. And if you get that, you will be sure that your results will have coverage, no matter what is the true value in nature of this unknown nuisance parameter. So this is easier to be told in words than to be done. And in these slides here, which I'm not going to describe in detail now, you have hopefully a clearer explanation on how you do it in practice. Okay, so you have basically to replicate possible universes, each with a different value of the nuisance parameters, and repeat the measurement on those and make sure to take the most pessimistic case, the one that makes your inference least precise. And if your inference has coverage in the least precise case, then you will have a coverage for all possible value of the nuisance parameter. And this also has its own drawbacks, because you get worse results in the sense that they are less precise. So there is a lot of work to obtain something that is less sexy, at face value at least, even if it's probably more correct. And this thing gets much worse and worse in the high dimensional problem. So if you have many dimensions, if you have many nuisance parameters, chances are that by putting yourself always in the most pessimistic case of those nuisance parameters will make your final inference almost non-informative. So your measurement will have huge uncertainties, which cover, yes, they will cover, but they do not bring much information. And of course, the other drawback is that it takes a lot of work. A shortcut for that is to reduce the dimensionality of the likelihood using the so-called profiling, which consists basically in moving from the full dimensional likelihoods here on the left, which depends on the full set of physics parameters and the full set of nuisance parameters, to a simpler mathematical structure, which is called the profile likelihood. And it's simpler because it has fewer dimensions, because you have basically derived your likelihood with respect to each of the nuisance parameters. And the profile likelihood is no longer a likelihood, so it does not have mathematically the same properties of the likelihood, but it behaves, quite decently yet. So it is used for inference in frequentist statistics in high dimensions. And so one generalization of the Feldman-Clausen procedure can be applied to this case of the profile likelihood. And here I show you an attempt at actually executing that in a problem with your data. But unfortunately, I do not have time now to go through that. So here is a very simple and simplistic roadmap on how to deal with that. I hope it will be clearer to you once you digest all the details that we went through today. And now let me briefly touch on the last topic of this lecture. I hope I can use another 7 minutes maybe. So this is hypothesis testing. And basically it brings us back to one of the first slides I have shown you, right? So you have a distribution of data points shown here, and you have a model for your background, which is this dashed curve. And you want to know if your data follow properly the background model, or maybe if something could be there suggesting the presence of an anomaly. An anomaly can be a signal, or can be, you know, a problem in our, you know, instrumental apparatus, whatever. Okay. So how do I quantitatively evaluate that? Well, in frequency statistics, I use p-values. So p-values are random variables, or variables of the data, and they do help answering this question. And they have also a very funny story of their origin, which is linked from here. So in the business of the p-values, you are trying to see whether your data favor one hypothesis or the other. What is an hypothesis? An hypothesis is, you know, a possible configuration of the thing you're trying to measure. So in very generic sense, you will have a null hypothesis, so the background only. So whatever you expect is there only. And it's read here, it's P of X given background. And then you may want to test a signal hypothesis or an anomaly hypothesis, which we call P of X given S plus B. So given that if nature would have a signal there, how my data would look like. So you have these two hypotheses, and then you need a quantity that is measurable in your data that can distinguish about them, right? So if I'm trying to see a signal in an invariant mass distribution, maybe the signal yield resulting from a fit could be that quantities, because this number is distributed differently. If I have signal in my data, it might have a distribution that follows this blue thing, or if I only have background, it will be something centered around 0. Of course, this quantity that I choose should be able to distinguish the two hypotheses. If I take the phases of the moon, you know, the phases of the moon will be the same whether I have a signal or not in my data. So it's not a valid, very useful thing to distinguish signal and background. Therefore, I have chosen my two hypotheses. I've chosen a quantity that is able to distinguish them. And so I generate the distribution of these quantities using Monte Carlo simulation. And I have these two curves here, the red one and the blue one, okay? And so far, I have not yet observed the data. I just have some possible distributions of my data in the two different hypotheses. And of course, when I will observe the data, which is in the x-axis here, if I observe something that is very much to the right, I will be led to think that is probably suggesting the presence of a signal. Whereas if I observe something that is very much to the left in this metric, I would lead to think that maybe the signal is excluded. So I look at the data and suppose that my observation is this black vertical line here. And this black vertical line in this particular experiment has fallen right to the right, to the signal-like region of my expectation. And therefore, I will use, if I'm trying to discover a new effect, okay, if I'm trying to use this observation to argue that there is an indication of a signal, the way I use to quantify that is to take the integral of the tail of the red distribution, which is shown here. So integral of the tail of the background only distribution as a measure of how my data is compatible with a signal or not. Because of course, the rightmost is my observation and the smaller will be this integral of the tail, right? Because I'm going away from the background distribution. And therefore, small values of this integral will suggest that my data are incompatible with the red distribution, suggesting that I'm possibly discovering a new effect. Is that clear? It's important that this is clear. So if it's not, tell me, and I will try to repeat with different words, hopefully. Yes, maybe this is clear. And if instead I'm trying to use the data, so in this case, I was trying to use the data to discover a new effect. But if instead I'm using the data to exclude the new effect, then I have to take the, the other tail, the background-like tail of the signal distribution, the left-hand tail of the blue distribution. The smallest is the area of the tail, and the strongest will be the exclusion of the signal brought by my data. Okay? So this is exactly, Popperian logic. So you cannot prove that an hypothesis is true, it's just that it's false. So you discover a signal by excluding its absence. And you limit the existence of a signal by excluding its presence, okay? And the p-value does that. So you have to remember that p-value is not a probability, although it's the integral of a PDF. But since it's the integral of a PDF that you do after looking at your data, its probabilistic interpretation is a little bit troublesome. So it's not a probability, and it does not express the probability that an hypothesis is true or false. Right? It just expresses a quantitative of your data with a certain hypothesis. This is a one-slide recap, and I think we should probably end here. There are additional details, but I don't want to steal much time for the next lectures. I'm sorry again for this lecture today being a little bit rushed. I didn't plan well for my timing.
Okay, so thank you very much, Diego. As you said, we'll have the slides available as a reference, and of course there's the opportunity to get in touch if someone has a specific question about something you've shown. But are there any immediate questions for Diego? Either in the chat, or you can open your mic. If not, thanks again, Diego, and it's very much appreciated. And we'll no doubt be in touch soon about one thing and another. So thank you, and
Right.
we will move to the next lecture by IFA in a few minutes. So,
Yeah. Thanks to you, Jim, and all the organizers, and thanks to the student. Please do not be shy. Send me emails. I will be happy to answer any question or to point to any additional references. In fact, at the end of these slides, I had some references that you will see once I give them to Jim.
Yeah. Okay, that's great. Okay.